Great. Thank you. Thank you, Abby. Thank you all for taking this time a week before Christmas to join us for what should be a very informative webinar today. So thank you again for taking the time to join us. Our speakers are no strangers to our group. So we have both Kelli Allen and Sandra Soto speaking today to us about the optimization of clinical trial design. So Dr. Soto from our School of Nursing is going to start with her presentation, which is titled Multi-Phase Optimization Strategy and Applications to Intervention Development, Optimizing Interventions to Allow for Smaller Sample Sizes. So Sandra, whenever you're ready, I think you can share your screen and proceed when you're ready. Thank you.
Thanks. Can you see my screen? I assume so.
We can, yes.
Okay, great. Thank you, everyone. I do have a cold, so excuse me for coughing or clearing my throat a lot, or maybe sneezing. So today, yes, I will be discussing the multi-phase optimization strategy, which is also referred to as MOST, and its applications to intervention development. I want to start by talking about the classical approach to developing interventions. So typically, we as researchers will test multiple intervention components simultaneously in one package. And so we piece together our best intervention based on the literature, theory, prior experience, and prior evidence. And we might pilot test this intervention and then take it to a clinical trial. But basically, we're testing the whole thing together. So, for example, my team and I got together a couple years ago to think about how to add on to the existing Walk with Ease program, or in Spanish, it's called Camina con Gusto. Um, so the Spanish version is the same as the Walk with Ease version. So it's a 6-week walking program for people with arthritis that's delivered using a workbook. Here's a picture of the workbook in Spanish. And weekly emails that provide summary of the information contained in the workbook. It provides education on physical activity and how to do it safely with arthritis. It also uses self-evaluation and contracts that you make with yourself and planners to build a walking habit. And although Camino con Gusto, or CCG, has been shown to increase walking and relieve arthritis-related symptoms, its limitations are in its brevity. So again, it's only a 6-week program, and its potential impact on physical activity maintenance is unknown. So we wanted to add to this program to enhance its ability to promote maintenance of physical activity over the long haul, so over 6 months. So for using this classical approach, we might think, okay, what can we add to Camina con Gusto? So we could add pedometers, which, the literature shows that pedometers might be effective in promoting physical activity. So we could throw those in. Also, being that we're working with the Latino community, we think about social support. So we could think about creating groups using the WhatsApp application. So it's a texting app that is very popular among Latinos because it allows you to text for free internationally. So we could create groups in WhatsApp so that people can provide social support, social accountability, other social influences to one another. We could also consider adding in a health coach. So a lay health coach or a promotora. It's a model that's been used a lot in Latino health behavior research because it's been shown to be effective to have someone of the community who speaks the language, who knows the lingo, who is basically equal to the participants delivering the intervention. So we could have someone come in and play that role. And then we could also think about, well, we are doing maintenance. So what about including something about habit formation? So we could create these habit formation videos where people learn how to do action planning, coping planning, all the things that we know relate to habit formation. The problem with the classical approach is, we don't really know. I mean, we have strong evidence, we might from the literature, from our prior experience, from theory, that all these things should be useful in promoting maintenance. However, the literature on maintenance is relatively new. We know how to get people to initiate physical activity, the big question right now in the field is how to get people to stick to it. So maintenance, especially among Latinos. We don't know much about what keeps them going, especially among Latinos with arthritis. There's even more questions around that. There's not much literature out there on Latinos with arthritis. But let's say we use this classical approach. We throw everything into this package, and now we're left with this black box, which is our intervention. And so we don't know, let's say we test this intervention, it's a black box, and it's effective. We see an effect on physical activity maintenance. Great. However, we don't know which of these components had a positive effect on Latinos with arthritis. Are all the components worth keeping, considering their cost and resources needed to implement the intervention as a whole? And when and if the intervention is scaled up and implemented across settings, does the elimination or the inevitable neglect of some or one or a few of the components affect its impact on the rest of the components? We just don't know. And so it would be great to know, listen, if you put this out into the world and you drop or neglect one of these components, this is what you can expect. All right, so what happens if we test this intervention package and we don't see an effect? Well, we don't know if there was an effect or an issue with one of the components, with all of the components, a few of the components. Perhaps one of them has a negative effect and it's offsetting the positive effects of the others. We're just not sure. So that's where we bring in the multi-phase optimization strategy, or MOST. It's an approach to carefully select the components that you're going to be including in this intervention package. So it helps identify the active components to create effective interventions. Now, I just want to note that using MOST does not mean you're replacing the classical approach. You're just taking a step back so that you're being more mindful and careful about what intervention components you're including in your intervention package. So using MOST allows us to streamline interventions, again, because we're not just adding all the bells and whistles that we hope will be effective. We're only including the things that we have a pretty strong idea that are going to be effective based on evidence for this context. It allows us to increase the probability of successful implementation and enhance its scalability, again, because we're only putting something out into the world where communities can pick it up and disseminate it, that aren't weighed down by things that might not be effective or might just have a null effect, so that we're only putting out there something that we know really truly does work. So let's say in this hypothetical example, we learn that by using MOST, actually pedometers were helpful in initiating physical activity, like the literature shows, but our primary outcome is maintenance, and it was not effective at maintaining physical activity. Great. Now we know. Now we can make the decision, do we want to tweak that intervention component? Do we just want to toss it? Pedometers aren't free. They're not expensive, but they're not free. And, it's too much to ask organizations to purchase and give away pedometers if they're not really doing anything. So we would know that by doing something like MOST. So the multi-phase optimization strategy has certain phases, and here they are. And I'm going to review these quickly now and then go over them in a little bit more depth in later slides. So we start out with the preparation phase, which we're laying the groundwork for optimization. And so in this phase, we're developing our conceptual model, we're selecting the candidate components that we're going to test, we might be conducting some pilot work, and we're identifying our optimization objective or objectives, which is just the criteria that we're going to use at the triangle phase here to either keep or toss components. I'll go over that a little bit more later. And then, And then we would move on to the optimization phase, which again, we're just going to be testing our intervention components. And then we would be deciding, again, what's going to stay and what's going to go in terms of the components that we're testing. And then finally, we would do that classical approach where we're testing the full package in a clinical trial. So we're going to begin with the preparation phase. So like I mentioned, this was a conversation that I had with that my team and I had, thinking about what could we add to Camino con Gusto. So again, everybody will receive the Camino con Gusto program because we don't want to replace it. We want to add to it. And this program was based on the social cognitive theory, which is why you're seeing that it targets things like self-efficacy, outcome expectations, behavioral capacity. And then we're thinking about these other candidate components and what they're targeting theoretically. What are we thinking that they're going to be doing? So the pedometer, we're calling it pedometer plus because it's not just a pedometer, it's also ways to track and log steps. So that's targeting self-regulation. The WhatsApp components, as I mentioned, are targeting social influences. The promotora will be using motivational interviews to target maintenance motives. So I didn't quite touch on maintenance motives. So because we're thinking about maintaining physical activity, the literature is showing that it's important to switch from external motivation. So a lot of people, when they start a health program, they start going to the gym, they start thinking about doing more physical activity. Their motivations tend to be external. So like, I want my promotora to praise me and give me some positive reinforcement for doing this. Or down the line, I want to lose weight. So this is all sort of external versus internal motivation, which is I want to walk because I enjoy it, because I get satisfaction from it, because immediately after I'm finished doing my walk, I feel really good and energized. So that switch is what's important, what seems to be important for maintaining physical activity. So having a promotora there to sort of walk participants through that. And then lastly, the habit formation video series, which would tap into habit formation. Okay, so that's the conceptual model. And then we, as I mentioned, we would be selecting the optimization objective or objectives to guide our decision making. And these are selected a priori. So we're choosing how are we going to decide later on which of these components need to stay or which need to be refined or be tossed out. And so we could do things like look at the p-value or effect size of each component. Now, they don't have to be like, needs to meet statistically significant standard of, 0.05, because again, this is just one component of potentially many. So it's not a full intervention. You're just looking at one component. So it just needs to signal that there is an effect here. It doesn't have to reach, that standard. So you could look at p-value, effect size. You could also consider things like cost or time. Maybe you understand working with community organizations that if this is going to ever see the light of day out in the real world, it can't be $700. It just cannot. And so maybe those things are things that you're going to consider like, okay, this is effective, but actually it's effective with everything else, all these other components. And now we're exceeding the threshold for what community organizations are willing to pay. And similarly with time, maybe you know that your participants aren't willing to give you, 3 hours a week or what have you. So these are all things that you would think about ahead of time with your research team. Okay, so after you've done all that, then you move on to the optimization phase, which is where you're conducting optimization RCTs or an RCT to test those components. So in thinking about how we would go about testing these components, there might be a couple ideas that you might have. So we're going to walk through some of these ideas for designs. So one could be you would test these components individually in individual experiments. So you would recruit a pool of participants and you would give half the pedometer and the other half no pedometer. And then you would recruit a whole nother batch of participants and you would give half the WhatsApp and the other half no WhatsApp and so on. That's one option. Another option would be the single factor experiment. So you would recruit a whole pool of participants, but then have subgroups. So one subgroup receives the pedometer, one subgroup would receive WhatsApp, one the promotora, one the habit formation videos, and then you would, have one subgroup that receives nothing. So that's an all one experiment. Another idea would be the factorial experiment. So factorial experiments, you have 2 to the n factors. And in this setting, the factor is the component. So we would have 2 to the 4 because we have 4 components, which would equal 16 conditions. And I want to show you what that would look like. So in a factorial experiment, we are setting the components at different levels. And typically there's 2 levels. So you would either set a level on, which I'm displaying here with an X, or off, which I'm displaying with a little dash. Or you could see a component could be set to high versus low. So maybe we could think about an example where you would have the promotora be a high versus low. So high contact, maybe 10 calls versus 5 calls, right? So you would be testing different levels. And so in this factorial experiment, again, as I mentioned, everybody receives camina con gusto or CCG. And then half of the participants will receive the component and the other half will not receive that component, and so on. So half will receive the WhatsApp group and the other half will not receive the WhatsApp group. So in a factorial experiment, what we're able to do is we're able to aggregate the effects of each of the components. And this allows us to test using ANOVA to test the main effects of each component and test the interactions between the components. So for example, if we wanted to see the effect of the pedometer, for example, we could see the effect average across all the levels. So I'm sorry, we could see the effect of the average of everybody receiving the pedometer, which would be conditions 1 through 8, versus the average of everybody not receiving this component, so conditions 9 through 16. So you'd be looking at the effect on maintenance of physical activity, and you would be comparing those two groups. So you're able to collapse those groups together and then collapse those groups who did not receive it together. So again, another example, if you wanted to see the main effect of WhatsApp on the maintenance of physical activity, you would look at the average of everybody receiving this component versus everyone not receiving this component. And then to see the interaction between components, so you would, for example, if you wanted to see pedometer by WhatsApp group, so that interaction between those two components, you would be asking, is the effect of pedometer when the WhatsApp group is on different than when the WhatsApp group is off? And you could actually then take a look at multiple higher level interactions with the rest of the components. It gets more complex than this, and this is already pretty complex. And I'm not a statistician, so I'm not going to pretend to keep going, but I hope that this gives an idea of how you are able to look at the interaction between components. So going back to our ideas for, which design we could do, I went and I pulled this example from a paper that used 6 components. So the example that I just showed you was 4. So this one used 6 components to show what the sample size would look like for each. So for the individual experiments, again, this was the experiment where we're pulling a sample and we're giving half the pedometer and half not the pedometer. And then we're doing a separate experiment with brand new participants and we're testing WhatsApp versus no WhatsApp and so on. So in this design, we would need over 4,700 participants to test these 6 components. Okay, that's in my world, that's a lot. And then the single factor experiment, so this was where we have the one sample and then we give a subgroup, the pedometer, a subgroup, WhatsApp, a subgroup, each component, and then a subgroup receives nothing, and we're comparing them to each other. In this case, we would only need 2,700, just over 2,700, which is much better than the individual experiments. And then what happens in the factorial experiment is we then, we have 64 conditions, which is a lot logistically to handle from the researcher side. But in terms of the sample, we only need approximately 800 participants. So that is way better, way more doable than the 4,700 or the 2,700. So again, going back to the sample size issue, it's obviously a much more achievable approach to use the factorial experiment, but there's one other benefit of this design, which is the ability to test interactions between components. You're not able to do that with the other 2 designs. And again, this becomes important because even if one component does not show a main effect by itself, it does not seem to be effective on your primary outcome. But when maybe, perhaps, you could see some synergy happening with it between it and another component. So let's say the habit formation videos don't seem to be doing anything on their own, but when you see the interaction with the promotoras, you do see that there's something happening there, and so you might want to keep it. So it would be important to be able to test the interactions between the components. I do want to make a note. So in this example, if we were to do this experiment with our 4 components, we did do a sample size calculation, and we would have needed 240 participants. 16 conditions. But I want to note, again, we are comparing the group of conditions that receives the component versus the group of conditions that do not. What we are not doing is a multi-arm RCT where we're comparing the row, so one condition versus another condition. Because if you see, I've added the sample per condition that we're going to need to be able to do this factorial experiment, and we need 15 per condition. So if we were to do this like a multi-arm RCT and compare the conditions versus each other, rather than collapsing the conditions that receive one component versus the collapse of those who don't, the grouping, the aggregation of them, we would then end up comparing 15 people versus 15 people. So a total of 30. That's not going to get us anywhere. That's not going to show us anything. That's not enough samples. So that's not what we're doing here. If we wanted to do a multi-arm RCT, we would need way more participants per condition to be able to test these and compare them to one another. Okay, so after we've done our optimization RCT, which again I haven't mentioned. So the optimization RCT does not have to be a factorial design. That's just the example that I'm providing that I'm more familiar with. It could also look like a SMART design, which Kelli will cover next. It could be a number of designs, a JEDI, which is a just-in-time intervention, different ways that you could approach it. It doesn't have to be this factorial design. This is just one of the more common approaches to use. Okay, so then after we've done our optimization, RCT, whatever that is, a SMART or a factorial design, we would then go back to our optimization objectives. So what were those criteria? What was that criteria or what was that criterion or criteria that we decided? And then we would look at these components and decide, okay, what needs to stay? What needs to go back to the drawing board? Can we move forward with something together? And if yes, we can move forward, then we go and do our classical approach of testing our RCT. So we would evaluate this intervention component. And maybe then, we would only be including the things that we saw, look like they should be included. So maybe with our optimization, factorial design, we saw, nope, pedometer does not need to be in here. So we wouldn't include it in our final package. And then we would know, we wouldn't have this black box. We would know exactly what's going in here and how things should be behaving when we test it as a package. So I do want to mention that the literature on most it's common in other disciplines, not necessarily our discipline. So we see a lot of things happening in cancer, especially some weight loss, but there's not much happening in rheumatology or musculoskeletal areas. And so I just want to put that in as a plug. But just some key takeaways. So most is an alternative approach to developing interventions that doesn't, that helps you be more careful and mindful about what components you're integrating into an intervention package. The phases of most there are several. And then again, there's a huge gap in rheumatology. And I want to finish by acknowledging my team. And here's some resources. Thank you.
Okay, thank you. And we will hold questions until the very end. But next, we will transition to Dr. Kelli Allen. And the title of her portion is Intervention Optimization and Heterogeneity of Treatment Effects.
All right. Hello. Am I good? I know I need to make it a
Yep, we can.
presentation view.
Yep, we can see your screen.
Okay. Oh, I just switched to presentation view. And I can't see you, but are we good?
Yep.
Okay. All right. So I'm gonna take maybe step out in some ways and step in some other ways, and talk about some different ways, approaches to intervention optimization and understanding heterogeneity of treatment effects in the context
Dr. Allen, sorry to interrupt. I don't know if this is the same for others, but from what I see of your screen, it's not in presentation mode.
Okay, so here's what's happening is, let me switch here. Oh no, I can't do that. I've got one of those weird things going on where I think it's showing you what's on my laptop and not on my monitor. I don't know if I can fix that. Let me try. I'm thinking I always have trouble with this. Did that work or no?
No, it came back and it's looking the same.
Okay. Let me do this.
We can see the slide. It's just not the full screen.
Yeah. There's probably some way to do it and swapping like which is the main screen or something like that. But I think what I'm going to opt to do is something I think will be quicker. And that is I'm going to unplug from my monitor and switch to my laptop camera. Hopefully that will not disrupt things. Give me just a second here.
It looks good now, by the way.
Can you hear me? You can't hear me.
I can hear you,
Yes, I can hear you.
and the slide is full screen.
Okay, awesome, awesome. And let me see if you can actually, I can let you see me too. Let's see how we do this.
Hey, 3 for 3.
Oh, it just went away. Hold on. There we go. Okay, good enough. Not as good of a camera, but it'll work. So it looks okay for you all?
Yep, looks good to me.
Okay, great. All right, so I'm going to talk about some different aspects of intervention optimization and heterogeneity of treatment effects in the context of trials. And see how I advance here. There we go. Okay, so a couple learning objectives here today. One is just to be able to recognize heterogeneity of treatment effects, or which I'll abbreviate HTE, in rheumatology clinical trials. And then second, to describe methods for addressing HTE in 3 broad ways. One's in intervention development, which is related to what Sandra just talked about, and then also in analysis and different types of study designs. So first, let's talk about what is HTE. And I'm showing you two graphs here. The top one is showing a situation where you have kind of a homogeneous treatment effect across individuals. So on the bottom, you see some patient characteristic X, and on the Y, you're looking at the treatment effect. And you can see in the middle, the average treatment effect, and then looking at all the dots, which represent individual study participants, there's a pretty similar spread around the average treatment effect, regardless of what level of X, that patient characteristic, you're looking at. Okay. That's probably atypical. What is more typical is something like we see on the bottom. It may not look exactly like this pattern, but what we see is some different impacts of the treatment across levels of patient characteristic X. So here we have the same average treatment effect middle compared to the top one, the top graph. But you can see if you just extracted, for example, that patient sample between the purple lines, there is actually a higher average treatment effect. But you wouldn't pick that up just looking at the average treatment effect. Okay, so those dots are spread in different ways around the average treatment effect, depending on the level of patient characteristic X. So that's just a general idea of what we mean when we talk about HTE in the context of clinical trials, or it could be observational studies as well. But again, this is just one example of a pattern you could observe. There are a couple of different overall categories we think about with HTE. The one on the top I'm showing is something called a quantitative interaction. So here, there is large improvement in response to treatment for some patients and little improvement for others. So if you look at subgroups 1 and 2 and the different treatments, they both have a similar response to treatment 1, but for treatment 2, subgroup 2 has a higher response. So that's one thing you could observe. You could also observe that what we think of as a qualitative interaction, where one treatment works better for one group and the other treatment works better for another subgroup. So you can see that represented here. For subgroup 1, treatment 2 is better. For subgroup 2, treatment 1 is better. Okay. So again, just some more examples of what these differential effects might look like. So are there differential effects in rheumatology trials? For sure. And not every paper you look at is going to be focused on that. One of the ways you can get some idea of how heterogeneous the treatment effects are is just look at the confidence intervals around the estimates. If it's wide, that's some indication that there is some heterogeneity, but what it is usually not a primary analysis that somebody's going to do for a clinical trial. A couple of examples here that I'll talk about more later. The one on the left is from a trial of tocilizumab in RA. And I'll give more details about this later, but you can just see over time, this is 52 weeks of treatment, and you can see the different trajectories of patients. These are DAS scores over time. And then for the second one is results from a clinical trial our team conducted, looking at 2 different exercise-based therapies for knee osteoarthritis. And these are WOMAC scores, so self-reported pain, stiffness, and function. And you can see each line there represents an individual patient trajectory from baseline to 4 months. And you can see there's just a lot of heterogeneity. Overall, in individuals, if we look at the mean score in the trial, the primary outcome was that basically everybody got better. The people got better in both treatments, not that everybody got better. But you can see that certainly not every patient got better, right, over time with either of those 2 interventions. So let me talk about addressing HTE with intervention designs, and I'm going to talk about particularly adaptive designs. And this is a little bit different from a SMART trial, but there are some similarities. So with an adaptive design, you come at it with a kind of a guess that whatever your initial treatment is, probably it's not going to be adequate for everybody. And so in this example, what we were studying, this is for knee osteoarthritis, and we started out with a home-based kind of light touch intervention and followed people for 3 months, look to see, are they making clinically relevant improvements in pain and function? If yes, that's great. We let them keep going. But we expected not everybody would. And so we had a plan, this is the adaptive part, for layering on some additional intervention components when people did not make clinically relevant improvement. And so our second step was some telephone-based activity coaching. We followed people for another 3 months, again, looked at some look for clinically relevant improvements in pain and function with an established measure. And then if people had not made improvement at that point, we sent them to physical therapy. So in this particular example, our adaptations were, again, layering on things and a little bit more intensive and specialized kind of interventions to hopefully get most people to where they're seeing clinically relevant improvement in function. There are different ways you can do adaptive interventions, but the general idea is that you are starting with something and then adding or changing to something else based on patient response, okay? Which again, a little bit different from SMART design, and I'll differentiate that in a minute. So most is another way that Sandra just talked about. I'm not going to address that since she just did, to kind of get it with the intervention design. And so I'm going to switch already here and start talking about addressing HTE in the analysis phase. So typically the way people do this is these one variable at a time interactions. So you do a clinical trial and you see their overall effects and you want to know, do they differ by age? And so you can put an interaction term in your statistical model and try to find that out. It's not an approach that should not ever be used, but there are some key disadvantages to it, or key limitations. One is just potential for false negatives due to low statistical power. Most often trials are not powered for this. Sometimes you'll see trials that have like one a priori variable of interest and will have some power associated with that, but I would say that's the exception rather than what's typical. Obviously, you can only explore a limited number of patient characteristics, also due to sample size and statistical power. And then along with that, we often don't have good prior theory on what those effect modifiers can be. So, let's say, well, we think it might be age, we think it might be socioeconomic status or whatever we pick, but we don't really know. Sometimes you might, and so that's a good time to use this sort of approach. But you have to come at it with understanding that we might know not know what's really driving effect modification. This can be incongruent with clinical decision making. So if somebody's trying to decide, clinician is trying to decide what the best therapy is, often it's not like, oh, well, if they're over age 65, this is going to be best. If they're underage, this is going to be age 65, this is going to be best. And then related to that, it misses potential effects of multidimensional subgroups. So maybe it's older women, for example, who do better with some sort of therapy. Again, not that this approach should never be used, but just wanted to bring out some of those limitations. So this paper here, and I'll put the reference again at the end if you want to pull it out, is called the PATH statement, the predictive approaches to treatment effect heterogeneity. I think this is a useful summary of these types of approaches. And what they're doing in this paper is providing looking at different approaches that take into account multiple relevant characteristics simultaneously. Okay, so rather than that one variable at a time interaction approach. And they break things down into three groups of types of analyses, or three categories for doing this. And so the first is risk modeling. I don't see this done super commonly, and maybe in other fields, but not in rheumatology or musculoskeletal conditions. And here you would develop a multivariable model that predicts risk for an outcome, and you can do that either externally in another data set you have, if you have that, or within the trial. And then you would apply that model to stratify patients in your trial and then look at risk-based variation in treatment effects. Okay, so I think an interesting approach, but again, I don't see that done very often. The next one is broad category is effect modeling. And in this, you would develop a regression model within your trial data, and that includes the treatment assignment, of course, potential risk predictors, and then sometimes an interaction term. And you're trying to look at how much of the average effect is modified by the baseline predictors of interest. So this is a flexible approach, but it's also prone to overfitting and false discovery, again, due to those sample size issues we talked about earlier. And then a third broad category of these types of analyses are data-driven approaches, latent classes, machine learning, et cetera. And this is an approach our team has done in a few studies, and so I am going to give an example here today. But actually, this is not our team study. I'll talk about that in a minute. This is the first study I showed earlier, a study of tocilizumab in patients with RA and moderate to severe active disease. What they wanted to do within the trial was identify factors associated with heterogeneity, including biomarkers and patient characteristics. And so what they did was they used latent class, which is a pretty well-established method, to first identify those treatment trajectories. And you see that in the graph on the right, those individual predictors or individual patient trajectories. And then on the right here, you see the three latent classes that emerged from the data. Now, unfortunately, they didn't find any really factors that popped out in terms of easy demographic characteristics or clinical characteristics that would say, okay, if you have this, then your trajectory is going to look like this. And that would be nice, right? That would be what we're all looking to do with these types of analyses, is understand how we can tailor clinical care. They did find that the groups differed in some biomarkers, and so for example, creatine reactive protein was higher in group 3, and tender joint count higher in group 1. So some indication of what might be going on clinically, but not quite at the place where these specific analyses could be used to definitively guide care. But I found an interesting example to look at. And then another example from our team. So this was a study in which we compared physical therapy and internet-based exercise training relative to a waitlist control group in people with knee osteoarthritis. So this is an overview of the trial design here. On the left, you see the graph I showed earlier of these individual patient trajectories and WOMAC score from 0 to 4 months. And we used a machine learning approaches. We've actually used a few different types of machine learning approaches to explore multidimensional subgroups. And I'm going to give you just one of those examples today. The potential predictors that we included in our model, you can see here a lot of demographic characteristics, some health-related characteristics, some of which are osteoarthritis related and some of which are more general. And then we also had some baseline characteristics related to activity, since that's a focus of the analysis. So here the example I'm showing here is something called qualitative interaction trees, or QUINT. And here we're comparing both the two active treatment arms, the internet-based exercise training program, or IBET, and physical therapy. This particular method, QUINT, is one that is designed specifically to compare or to look at factors that predict response in two active treatment groups. So in this particular analysis, we don't have the control group, and we did that in a separate paper that I'm glad to share as well. So here we're splitting patients based on characteristics that maximize the treatment response based on the subgroup they're in. So the first split was for body mass index, or BMI. And one particularly, I think, interesting finding is that for people with the lowest body mass index, so less than 24.3, that is the group that's on the far left red box, they did better with internet-based exercise. And you can see at the very bottom of the slide, those are mean WOMAC scores. So you can see what I would say is a clinically relevant difference between those groups. So for that group, the mean effect in IBET was a change of about an improvement of about 9 points in WOMAC versus about 2 for the PT group. Okay, and let me just back up and say that the red boxes are subgroups for whom internet-based exercise training was better, and green is when IBET was better. And then if you look on the opposite side of that tree for BMI over 24-ish and the highest duration of osteoarthritis symptoms, so the far right green box, there was definitely a better effect, a change of about 10 points for people who, in the context of physical therapy versus about 4 for IBET. And then you can see in the middle, there were some differences in those subgroups based on social support. And to me, those are a little bit harder to interpret, which is a risk of these types of analyses, is that, sometimes things make a lot of sense clinically, and then sometimes like, I'm not really sure how that plays out. And I think we have a mix of that here. Two messages that I've put here that I think are helpful and are pretty clear from these analyses is that people with the lowest BMI did well with the home-based program, and then people with high BMI and the longest duration of symptoms did well with PT. To me, those are pretty clear kind of things that could be used to guide treatment. However, as I mentioned, these are exploratory. What I think they're really useful to do is to help design future clinical trials. For example, trying to find variables that would be meaningful in terms of stratification or powering for an interaction, or tailoring the treatment at the outset. So I think there are a lot of ways that that you can go, and this is a great method for using data you have or that are out there to understand what might be the next step in understanding this treatment heterogeneity. Okay, another aspect of analysis is thinking about dose as a factor in heterogeneity of treatment effects. And let me say that I am a firm believer in intent to treat analyses for main study results, right? We want to understand, in general, people who are exposed to a treatment, regardless of their adherence, does it improve outcomes? However, I think it is also helpful to explore, if you do see heterogeneity of treatment effects, does the things differ based on the dose of the intervention received by participants? And here's an example. This is from the same trial that I mentioned earlier, and what I'm showing here are changes at 4 months in the dark blue, 12 months in light blue. This is only for the physical therapy group, I should say. This is changes in WOMAC. If the bar is going up, it mean worsening actually, and then improvement is going down. So to summarize what we're showing here, people who didn't, the PT groups got a little worse, or PT sessions. People who attended 2 to 5 improved WOMAC scores. People who attend 6 to 8 improved the most. So just some indication that there is heterogeneity in what we saw as the overall treatment effect based on dose of the intervention. Perhaps not overly surprising, but I think helpful to see, because one thing that tells us is that the overall effects of the physical therapy intervention are probably being muted based on people who basically didn't engage. Okay. I'm going to say just a little bit about SMART trials. I don't know if we mentioned at the outset, but Sandra and I are kind of repurposing our talks from ACR Convergence, and there was a whole separate talk on SMART trials. I'm not going to completely replicate that, but I think it's an important aspect of looking at heterogeneity effects in study design. So in these types of trials, participants are randomized at each stage to a set of treatment options. So how does this differ from adaptive designs, right? We talked about later about adding treatments or changing treatments midstream in the study. Here, the big difference is that they're not based, well, they are based on treatment response, but they're randomized, whereas with an adaptive intervention, they are not. So in this example, we have patients who are assigned to IBT, which is, oh gosh, what is that? It's like it's behavioral therapy. This is a weight loss trial. And then they are randomized to for a certain period of time. They look to see if there's responders, and then responders are re-randomized to augment IBT or switch to ACT. So this is a little bit more of a complicated one. You can find even more complicated SMART trials, but the basic idea is that you do look at response to an initial therapy, and then you will re-randomize people to different treatment options often based on response or non-response. Okay. So that's just a little bit about SMART trials. And let me switch a little bit here and talk about, actually, that's more of a study design. Another design you can use is just a design really to assess an interaction. We talked a little bit earlier about the fact that we often don't know what the biggest factor of interest might be, but sometimes we do. And I think that's a direction we want to head. In this situation, or this study here, well, this is our general illustration. I'll give you an example on the next slide. What we're saying is that we do have a good idea of what our important subgroups might be, some phenotype or genotype, and we will split them at the outset of the study. So men and women, or this genetic factor, subgrouping based on that. And then they're randomized within those subgroups to the active treatment or the placebo. And then the primary analysis is on the treatment by phenotype or genotype interaction, okay, not the treatment effect overall. And here's an example of that. This is a study of oxcarbazepine in pain, look about, what is it? It's peripheral neuropathic pain. And so what these researchers thought, based on prior researchers, was that this phenotype, they call it irritable or non-irritable phenotype, is based on quantitative sensory testing. They thought maybe the medication effects would differ based on that. So they did the quantitative sensory testing, split people into the irritable and non-irritable phenotype. They were randomized within those groups to oxcarbazepine or placebo. This study also had a washout period and a crossover design, which is a whole different kind of thing. And they actually did find that the medication was more effective in the irritable phenotype group. Now you look at this type of study and you think, oh my gosh, that must have been like a huge sample size study if they're going to randomize within those two subgroups, but it wasn't. It was like, I think 97, about 100. And so just a type of design to keep in mind that it may be more feasible than we think to do studies of this nature. Okay, so those are my key points. Let me just summarize. Be aware of HTE when you're reading rheumatology or other clinical trials research. Again, as I mentioned earlier, one way to do that is just look at the confidence intervals and try to understand what might be going on. Plan for evaluating HTE rigorously when you're designing your own trials. There's lots of ways to do that. And then finally, if you're a clinician, try to consider HTE in delivery of care. Unfortunately, we often don't know what those factors are that are going to bring about the heterogeneity, but educating patients as much as possible on that is helpful. All right, let me end here. Oh, here are the key references. I'll leave this up for a minute. The one at the top is a general review of personalized pain treatments. The second one is that path statement that I mentioned, and then the third one is a study by our team. And thanks to my research team and the funding sources, and the QR code goes to our CCCR if you're interested in grabbing that real quick. We'll end there.
Okay, thank you both for an excellent presentation. We do have time for questions, and we're happy for you to unmute yourselves and ask those questions, or if you wanted to put something in the chat, I can be monitoring that. I wanted to start off thinking about the most paradigm. Can you talk a little bit about whether there are any kind of special analysis consideration? So if you were working with, say, a biostatistician who wasn't specifically familiar with most, Is there anything special they need to know? Do you need to consult with a certain group? Like what are some considerations in that regard?
Yeah, I think in terms of the power analysis, it might look a little bit different. I know that the woman who pioneered this work, Linda Collins, has a whole team and they have tons of resources. And so some of those resources include the SAS and R packages for power analysis, for factorial design specifically. Um, so I know in terms of power analyses, yes, that's a special case. In terms of the doing the statistics, I mean it's an ANOVA. I don't know if there's a separate factorial ANOVA that behaves differently statistically than your run-of-the-mill ANOVAs. So I'm not sure if those two are different than what you could do without considering that this is a factorial design.
Okay, and just one quick follow-up to that. Have you had any issues with grant reviewers? Are grant reviewers generally on board with this, or do they question it? What's your experience been with that?
So far, so good. So I took this week-long workshop with Linda Collins and her team, and this was several years ago. And so several years ago, they were advising to not mention the factorial design in the specific aims page to highlight the most strategy, which is a little bit vague on a specific aims page, but not to dive in because then you start talking about like if it's 4 components, you have 16 conditions, and it just seems a little bit like, oh, what's this? But then she shared, I mean, pages of grant proposals that have been funded, ranging from Ks all the way up through R01s, UO1s, in between. So they are getting funded. Um, but again, this work has mainly been done in cancer and behavioral trials. When it comes to rheumatology in this field, um, I'm not sure. So I received a K to use most, but it was funded through the Institute of Minority Health and Health Disparities, um, which is a whole different beast from NIAMS. We have received different um, suggestions because of the reviewers at NIAMS that maybe Lee can talk about a little bit more, how maybe they're not as receptive yet to this
Well,
approach.
I don't think it's more that they're not as receptive to this approach. And it's a good question, Todd. I think what the thing is, like we're putting in a U award. Sandra and I got our co-PIs on an R34 that we originally put in the most approach. But as we've developed the work with this, there's been the recognition that we're developing a lot of these ancillaries to go in our online thing. And it understanding the components, and I think you've been in some of our ABC sessions where it's very interesting from a theoretical perspective or from behavioral science, like to understand, is the pedometer working on, just in this phase or not in the other phases, or does it work in conjunction with something else? But then that basically says, okay, then you create the optimal intervention and do another test. And so Elena really felt like, and we were, a lot of people in our ABC sessions were saying this too, that if we put in to do kind of a very interesting intellectual exercise for behavioral theory, they're not going to pay a big clinical trial U award funding for that. We needed to come in with kind of our best thing and do the trials. So I think it kind of depends what your question is. And we realized going into a clinical trial study section, they're not going to be interested in that question.
Yeah. Okay. Thank you. Other questions? I don't see anything in the chat at the moment. So I have a question for Kelli, and I think you touched on this, but could you maybe say a little bit more? You talked about kind of the multi-dimensional subgroups, and kind of the machine learning approach where you might end up with, people with a BMI above a certain amount and with this certain comorbidity and so on. Um, what do you do if you end up with a subgroup that's not really clinically explainable? What do you make of it if it sort of identifies this highly niche kind of group that, is not something that you would have expected or can explain?
Yeah, it's a good question. I will say that so far we haven't, which hopefully is encouraging. I mean, you all have done this was it with WeCan, um, or one of Steve Messier's studies, and I think the subgroups there made sense. We would use a couple different approaches in the study that I just talked about, one of which include the attention control group, and it. So we have it that which hopefully means that using these type of approaches that will bring out things that are real and that patterns that make sense. But you're right. It could bring out something that either just doesn't make sense, I guess, or that is not really helpful,
Hmm.
right? Like so, and the case that the one example I showed you, I think even the one that was the multidimensional that came out that older adult or people who were not older adults, it was longer duration of osteoarthritis symptoms and higher BMI. That makes sense. Like that makes sense to me that those are people who, high BMI often goes with comorbidities, right? So people who are sicker and have had disease longer, it makes sense that they may need a little bit more guidance, a little bit more support for their activity program. So I don't know that I can answer your question about what you do because we haven't had that situation come up, but there are different approaches you could take. Like if you could narrow the scope of your analyses. So we have taken the approach so far in putting in all the variables we have. And because saying we really don't have a sense of what might be causing the heterogeneity. So we didn't put things in that didn't make any sense at all. But we put anything that clinically or from behavioral theory we thought might have some plausible pathway for influencing differential treatment effects. So we've done it that way. But you could say, okay, I'm really most interested in these like 5 or 6 or 7 factors. And that's what you put in your model. You could do it that way. I think that's not the typical approach because usually when people use these types of data-driven machine learning things, you're kind of you're wanting to explore the black box. But I think you could do that. Like if you thought clinically, it would only really be helpful if I knew the potential effects of these 5 factors. I don't really care about the others. You could do it that way, I would assume. Although, these models they are really developed to be able to incorporate lots of different variables.
Great. So we are at time. Appreciate both of you sharing with us today, and I thank all of you for joining us. Wish you a wonderful Christmas and happy holidays, and Happy New Year.